Hello, everyone. I wanted to make you a video to kind of step you through um, the answers to the in-class worksheet. I'm also just going to send out the worked solutions to this as well, but we didn't have much class time on this, so I wanted to make a video as well in case it's helpful. So we worked through number 1 in class together, and I started you on number 3 here. So to start on number 3, we applied our common denominator to each piece up here. And the reason that we have to do that is um, because we can't take the derivative of a numerator and divide by the derivative of a denominator when we're finding our um, a derivative of a quotient, right? We need a quotient rule. Um, we cannot take an antiderivative by just doing the antiderivative of the top and the antiderivative of the bottom. That's not how it works. We need to figure out how to undo the derivative correctly. So we need to break this up. And so what you're going to do is you're going to distribute your common denominator here so that each thing in the numerator gets that common denominator. And then from there, we can combine what combines and simplify this. So we simplified it to x to the negative 2 plus 2x to the negative third minus 3x to the negative fourth. But we never actually got to finding the antiderivative of this in class. So let's work on that. So to do x to the negative 2, again, we're going to reverse the power rule by first adding 1 to our exponent. So negative 2 plus 1 up there is a negative 1. And then you need to divide by your new exponent. I just have a 1 out front, so I'm going to divide it by that new exponent of negative 1. And then I can add to that the antiderivative of my second piece. In order to undo this, I'm going to add 1 to my exponent because this is a power rule as well. X to the negative third, negative 3 plus 1 is negative 2. And I'm going to take whatever I have out front, that 2, and divide by negative 2, my new exponent. And then we'll do this again, minus 3 times x to the negative 4 plus 1. I'm adding 1 to my exponent. I get negative 3. And then I need to divide by that new exponent, which is negative 3. Because this is a general antiderivative, don't forget your plus c. And then we'll just simplify this quick. 1 divided by negative 1 is negative 1. X to the negative 1 minus 1 x to the negative 2 plus 1 times x to the negative 3. And again, we have a plus c out here. So that is our antiderivative. If your brain doesn't like to leave these as negative exponents, you can certainly write this as negative 1 over x minus 1 over x squared plus 1 over x to the third plus c. But you certainly don't have to either. You can leave it this way. All right, let's come back to number 2. How would we take the antiderivative of this guy? Well, first we need to bring this up to the top so that we can figure out how to use the power rule. When I rewrite this with algebra, I want to find the integral of 3 times x to the negative 3 halves power. I'm just bringing that x to the 3 halves up top. And I'm going to have my dx here. And so this says I want to take the antiderivative of the thing in here. And this is a power rule, and my exponent is not negative 1, so I can take the antiderivative of this by adding 1 to my exponent. Negative 3 halves plus 1 is negative 1 half. And then you have to divide by your new exponent. So we would do that 3 over here divided by negative 1 half. And dividing, oops, sorry, I forgot my plus c. This is a general antiderivative, so don't forget your plus c. And then we'll apply the algebra to simplify this. Remember that 3 divided by 1, negative 1 half. You're going to keep, change, flip. And this becomes negative 6 x to the negative 1/2 plus c. And again, if your brain doesn't like negative exponents, you can certainly write this as negative 6 divided by the square root of x plus c. But you don't have to move things around if you don't want. Okay, let's try number 4. I want the antiderivative of 8 over x plus 3e to the x. Now, especially with what we just did, you might be tempted to write this as 8 times x to the negative 1 plus 3e to the x, and then do a power rule on this. You might be tempted to do that, but take a look at that power rule on your integration rules list, and you'll notice that we can only integrate x to the n dx if n does not equal negative 1. But here I have a negative 1 in my exponent. And what that means is that the power rule does not apply to this function when my exponent is negative 1, because this isn't a power rule. So instead of rewriting that, how would I do the antiderivative of 8 over x? Well, this is the same as 8 times 1 over x. And are you okay with the derivative of ln x is 1 over x? And so this 8 out here kind of comes along for the ride. And the antiderivative of this is going to be 8 times the natural log of x. Now, Niall kind of mentioned this a little bit in class, and I was hoping to get some time to do this, but I just didn't. When you're doing the natural log, the derivative of natural log of x is 1 over x. So the antiderivative of 1 over x is ln x. We just have to be careful because you can't take the natural log of a negative number or 0. We have to make sure that the thing inside our ln is positive. And so in order to do that, we're not sure what x is. It can be anything. So we're going to put absolute value bars here on that x to make sure that we're taking the natural log of a positive number so that we can do this. And notice that x cannot be equal to 0 from my original here, so we don't have to worry about the case where x equals 0. That's not going to be included here. So this is going to be 8 times the natural log of x. That's the antiderivative of this part. And then the antiderivative of 3e to the x is 3e to the x, since the derivative of e to the x is e to the x, and that 3 comes along for the ride. And so I just need to add on my plus c because this is a general antiderivative. Okay. Number 5. Let's see. If I want to take the antiderivative of t to the 1/2 plus 1 times t plus 1, I'm tempted to do the antiderivative of this piece times the antiderivative of this piece. But remember, antiderivatives are derivatives, but in reverse. So when we do derivatives, do we just take the first thing times the derivative, or sorry, the derivative of the first thing times the derivative of the second thing? Is that how we do a derivative? No, if we have something with a t in it times something with a t in it, we need a product rule, which is complicated. And right now, we don't know how to undo the product rule. So what we're going to do instead is use algebra as our friend. Instead of trying to do this as one thing times another thing, I'm going to multiply all of this out and FOIL so that instead of two things being multiplied, I want a bunch of things being added. So when I FOIL this out, I get the first t to the 1/2 times t, that's t to the 3/2, plus the outside, t to the 1/2 times 1 is t to the 1/2, plus the inside, 1 times t is t, plus the last, which is 1 times 1, which is 1. And again, my integral is still here, and I need my dt here. These two things say, hey, you need to find the general antiderivative. I have not found any antiderivatives yet. I've just done some algebra to rewrite my original. So the integral notation needs to stay here. You only get rid of this interval notation if you take the derivative, because that's saying, yeah, I'm doing what you're telling me to do. And then you can kind of get rid of it and cross it off your list because you don't need it anymore. Okay, so there's no like terms to combine here. So we're ready to take an antiderivative. So now that we're taking an antiderivative, I can say, yeah already, and I don't need to rewrite the interval notation. So to take the antiderivative of these, they're all separated by addition and subtraction here. So I can just do piece by piece. Antiderivative of t to the 3/2. We're going to add 1 to my exponent. Adding 1 to 3/2 gives me 5/2. And you're going to divide by your new exponent. Dividing by 5/2 is the same as multiplying by the reciprocal. And then I'm going to add to that the antiderivative of t to the 1/2. Again, we're going to add 1 in my exponent, 3/2, and divide by our new exponent. Dividing by 3/2 is multiplying by 2/3. And we're going to keep rocking. The antiderivative of t, this is t to the first. So when I add 1, I get t to the second power. And I'm going to divide by my new exponent, which is 2. And I'm going to then take the antiderivative of 1, which is just my variable, which is t. And we're finding an antiderivative, so don't forget your plus c. There we have our general antiderivative. And I know that I'm done. None of these combine. I don't have any like terms, nothing, no algebra to do. So just put a box around it and walk away. All right, number 6. I want the general antiderivative of z squared minus secant squared of z dz. Okay, so I want to find the antiderivative of what's inside of here, right? The integral and the dz are my bookends. This is the function that I want the antiderivative of. So these are separated by subtraction. So I'm going to do the antiderivative of the first minus the antiderivative of the second. All right, z squared. How do we do the antiderivative of that? You got it, power rule. So we're going to add 1 to the exponent and divide by our new exponent. And then we will subtract the antiderivative of secant squared of z. If you need to go to your integral rules table for this, go ahead and do that. But this is one we can also kind of logic out. My derivative is secant squared. So what's my original? What function has a derivative of secant squared? Yeah, it's tangent. So this is going to be minus the tangent of z, because the derivative of tangent is secant squared. And that's my antiderivative. This is a general antiderivative, so don't forget your plus c. And then finally, in number 7, 3e to the 5x plus the sine of x dx. Again, these are my bookends, so I'm finding the antiderivative of all this inside. And everything in here is separated by addition, so I can do the antiderivative of the first one plus the antiderivative of the second one. The antiderivative of 3e to the 5x. Now, there is an entry in your table for what to do when you have a number times a variable inside an exponential. You can also do this in your trig functions, in your ln functions, really any of these. But if you have a 5x inside your e, let's think about this. I know the 3 is going to come along for the ride. And then if I had e to the 5x, I know the derivative of e to the x is e to the x. So to get an e to the 5x here, I needed to start with an e to the 5x. But let's think about if we take the derivative of e to the 5x. I would get e to the 5x times 5 from the chain rule. But I don't have an extra 5 out here. I just have a 3. which means that in my antiderivative, I need to divide by a 5 to kind of take care of that extra 5 that's going to pop out from the chain rule. Does that make any sense? So if you have an extra number in here, you need to divide by that number out front in your antiderivative to account for the extra version that pops out of the chain rule. So now that I have 3/5 times e to the 5x, go ahead and take the derivative of that just to make sure we get e to the 3e to the 5x. I'm just going to check myself on this because it's hard when you have more than just an x up here. So the derivative of this is going to be 3/5 times the derivative of e to the stuff is e to my stuff times the derivative of my stuff. The derivative of 5x is 5. And notice this 5 cancels this one, and I get 3e to the 5x, which is what I wanted. All right, and then we aren't quite done. We just kind of went through this first one. I'm going to add to that the general antiderivative of sine of x. To get a derivative of sine x, I needed to start with negative cosine. There we go. So we are going to have a negative cosine x here because the derivative of cosine is negative sine. This negative will cancel that negative from my derivative to make it positive in the end. And then I need to tack on my plus c because this is a general antiderivative. All right, and then we have a couple of initial value problems in here. I'll rock through these with you as well. We didn't get to initial value problems in class. I made a second video for you about that, so this will help you. That will help you with this. If you haven't watched that yet, you may want to go ahead and do that. But an initial value problem is when we are looking for an antiderivative and we have an extra piece of information that allows us to solve for a specific value of c. So a particle is located at the origin at time t equals 1 second and moves along the x-axis with a velocity v of t equals 6t squared minus t meters per second. Find the particle's position function s of t. Okay, so I want s of t, position. What I have is velocity, v of t. How do we get position from velocity? Well, because velocity is the derivative of position, that means that position is the antiderivative of velocity. And so we are just going to find the antiderivative of my velocity function, which is 6t squared minus t. And I'm going to integrate that with respect to t. That's the dt here. These are my bookends. This dt says that my variable is t. And so let's find the antiderivative of that. Well, they're separated by subtraction, so we'll do them one piece at a time. The antiderivative of 6t squared is 6 times, we're going to have to add 1 to our exponent. Adding 1 gets us to 3. Divide by your new exponent. And then I'm going to subtract from that. I'm going to add 1 to my exponent. T to the 1 plus 1 is 2. And divide by my new exponent. And then don't forget your plus c. And then we can simplify this if you like. 6 divided by 3 is 2. So this is 2t to the third minus 1/2 t squared plus c. That's my s of t, my general antiderivative function. But I want a specific position function. And I actually have an extra piece of information hidden in here. I know that the particle is located at the origin at time t equals 1 second. So that means that when time equals 1, my position is at the origin, which on the x-axis is 0, right? X equals 0 at the origin. So I know that my position at time 1 second is equal to 0 because my position is at 0 on the x-axis after 1 second. So now I can use this as my initial value to solve in my position function. So I know that when t equals 1, my position is 0, which means my position is 0 when I have 2 times 1 to the third minus 1/2 times 1 squared plus c. And so this is going to give me 2 minus 1/2 plus c, which means 0 equals 3/2 plus c, and c is negative 3/2. And so then I can put that together with my position function. So my exact position function is s of t equals 2t to the third minus 1/2 t squared minus 3/2. And then my last one says, given that my second derivative equals x to the third minus 2x plus 1, and that my f prime of 0 equals 1 and f of 0 equals 0, I want my first derivative and then my original function. Okay, well, I need my first derivative and my original function, but I'm given second derivative. How do I find my first derivative from my second derivative? Well, since the second derivative is the derivative of the first derivative, that means that my first derivative is the integral of my second derivative. Because again, antiderivatives go the other way as derivatives. It's a backwards derivative. And so to find my first derivative, I need to find the antiderivative of x to the third minus 2x plus 1. And you can apply your power rules. We've been doing this a little bit, so I'm going to kind of rocket through this. Hopefully that makes sense to you. And we'll simplify that, and we get 1/4 x to the fourth minus 1x squared plus x plus c. But this has a plus c in it. To find my exact first derivative, I'm going to use my initial value here. And the fact that f, oops, sorry, here we go. Let's try this. The fact that f prime of 0 equals 1 tells me that my first derivative is 1 when x equals 0 in here. These are all just 0, so 1 is equal to my c value. And what that means is then my first derivative exactly is 1/4 x to the fourth minus x squared plus x plus 1. That's my first derivative. And then we're going to repeat that process to find my original, because my first derivative is the derivative of my original. My original is the antiderivative of my first derivative. And so we're going to integrate what we just found for our first derivative. And we'll apply our power rules. We've got this. Right? I'm just adding 1 to my exponents and divide by your new exponent. I just did that repeatedly, and the antiderivative of 1 is just x. So I'll simplify this a little. We get 1/20 times x to the fifth minus 1/3 x cubed plus 1/2 x squared plus x plus c. And then I know that my initial value says that f of 0 is 0. And so I'm going to use that to find my exact original function. So 0 is what I get when I plug 0 in for my x. And notice this all goes to 0, and so I get that c is equal to 0. That's okay. C can be any value that it likes. And so my original function as my specific original function is 1 over 20 times x to the fifth minus 1/3 x to the third plus 1/2 x squared plus x with no c value at all. Okay. Hopefully that helps with section 5.3 homework. Let me know if you have any questions. I hope you have a lovely weekend, and I will see you next time.